Next paper will describe the work done in Professor Schwann's group at the University of Michigan, Ann Arbor. Co-authors are G.N. Kastanas and G.A. Sigdinos. And the title of the paper is Selective Oxidation of Methane to Formaldehyde over various catalysts. The paper will be presented by Kastanas.
Thank you. The title of today's presentation is Selective Oxidation of Methane to Formaldehyde over various catalysts. The work was performed at the Department of Chemical Engineering at the University of Michigan. Unfortunately, one of our co-workers, Dr. George Sigdinos, passed away 2 months ago, and I would like to take this opportunity today to acknowledge his very valuable contribution to our work and also dedicate this presentation to him. Now, the objectives of our research is to investigate methane interactions with oxide surfaces, modify the physical and/or chemical properties of the materials in order to achieve good yields of variable intermediates, such as formaldehyde and/or methanol. So far, we have laid the groundwork by working on typical support materials, such as silica, alumina, and magnesia. And for those of you who would be more interested in this aspect of our work, I would like to refer you to our recent publications in applied analysis and also Journal of Chemical Society Chemical Communications. Now, today I will focus in two particular systems: the modification of the properties of silicon dioxide by boric acid, and also I will talk about some very good yields of formaldehyde that we have obtained over iron molybdates. Currently, we are examining other support materials such as different forms of titania, and also working on iron tungsten vanadium system. Now, if one would try to plot the percent selectivity of methane towards useful products, such as ethane, ethylene, or formaldehyde, versus the percent conversion, then one can define a target area of both high conversions and high selectivities where a catalyst should lie in order to be commercially attractive. Unfortunately, so far the current status of the research on methane oxidation is more or less at an opposite direction, of either high conversions and low selectivities, or high selectivities with low conversions. Now, this next slide tries to put our today's presentation in this overall picture. First of all, we see that by modifying the silicas with boric acid, one can achieve high selectivities of formaldehyde over low conversion. Second, the iron molybdate systems are very promising materials in terms of yields of formaldehyde. Our reaction conditions are flow rates of 50 centimeters per minute, and we are using a dilute mixture of 10% methane and argon. We're also using the methane to oxygen ratio of 1. Steady state temperature range is 500 degrees C to 700 degrees C. The gas hourly space velocity is 3,000 r-1, and the pressure 300 to 500 kilopascal. Now, for the first part of the talk, the purification of silicas with boric acid. Boric acid is known from the combustion literature to be used as a flame retardant for propagation of the radicals that are very likely to be formed in the combustion processes. In our approach, we use the Ludox colloidal silica in a liquid form, ammonia stabilized, and we dissolve boric acid crystal on this Ludox. We adjusted the pH with either nitric acid or ammonium hydroxide. And finally, coagulation was both boric acid and silica was achieved at moderately low temperatures. We dried and calcined the samples furthermore, and we finally ended up with three different loadings of 0.7%, 2.56%, and 7.2% of boric acid. We did X-ray diffraction, and we found out that the co-gels were amorphous both before and after the methane oxidation reaction. X-ray photoelectron spectroscopy of both fresh and used catalysts showed boron present in an oxidation state of +3. The chemical environment was very similar to the one in the boric acid. Now this graph shows the effect of boric acid coagulation in the formaldehyde selectivity. We see that as the loadings of boron increased, the formaldehyde selectivity could be preserved at high levels at very good methane conversions. Now the blank Ludox support prepared by similar gelation method had a much somewhat lower formaldehyde selectivity than the boric acid compounds. The overall rate of methane reaction, when expressed per a small reactor per gram of catalyst a second, did not change much over the three different loadings that we used and over the temperature range that we employed. However, if we try to plot the rate of formaldehyde formation and express it in terms of mole per meter square of catalyst surface per second, we see that the high loadings of boric acid have an advantage. And also, we should point out here that the surface area of the co-gels decreases the amount of boric acid that we use. The 0.66% have a surface area of about 100 meter square per grams, the 2.54 of about 70, and the 7.20 of about 40 meter square per gram. Now, another interesting effect that we are observing is that the apparent activation energy for formaldehyde formation goes up with the percentage of boric acid and silica. We seem to be observing a compensation effect because the formaldehyde-free exponential factor goes also up with the formaldehyde apparent activation energy. Now the conclusions for the Ludox boric acid co-gels are that the coagulation of boric acid with Ludox silica can lead to the formation of stable and the high surface area boric acid silica systems. Boric acid and silica, also the boric acid co-gels and the silica Ludox support is prepared gel biomethod were exoamorphous. Boron is present at an oxidation state of +3, and we did not observe detectable loss of boron when we did XPS catalyst before and after the reaction. We were particularly concerned about that because more boric acid at the high temperatures used for methane oxidation is a liquid, but it seems that this preparation coagulation method, boric acid is well stabilized in the Ludox method. So finally, the effect of boric acid is to greatly enhance the formaldehyde selectivity and prevent further decomposition or oxidation of formaldehyde to carbon monoxide or carbon dioxide. Most probably, the primary methane CH4 activation must be occurring on silica sites. Now, for the second part of our talk, the iron molybdanes are known conventional catalysts for the oxidation of methanol to formaldehyde. So we wanted to investigate how this catalyst would perform in the oxidation of methane to formaldehyde. For the preparation, we used a solid-state synthesis, and our goal here was to form and preserve possible metastable phases and structure defects that are known to be beneficial for for selective oxidation. The characterization techniques that we used, first the VD surface area of the iron glutate materials was low of about 1 millisquare per gram. The X-ray diffraction proved that we formed in the iron molybdate phase. And also, we did X-ray photoelectron spectroscopy, and currently working on infrared spectroscopy and high-resolution electron microscopy. This slide shows the formation of the iron molybdate phase, and as we can see, by appropriately adjusting the iron to molybdenum ratio, we can form a highly crystalline iron molybdate phase. By lower iron to molybdenum ratios, we observe the doublet, and one of those peaks could be attributed to the 110 molybdenum trioxide plane, but the other one corresponds to the 1-to-1 iron molybdate. This table shows our results on methane oxidation, and as we can see, the iron molybdates had a very good conversion of 4% and produced about 198% selectivity of formaldehyde. As we increase the conversion, we were able to preserve this formaldehyde from further oxidation. And you see that at a conversion level of 27%, we can have a very good formaldehyde selectivity of 83%. Now let's see how molybdenum and iron performed by themselves. The molybdenum trioxide had a low methane conversion and not very good selectivity of formaldehyde. We did not attempt to increase the temperature of the methane oxidation of the molybdenum trioxide because it is known that molybdenum can volatilize at high temperatures that are being used for methane oxidation. Now, iron trioxide had a very high activity at temperatures even 200 degrees lower than the ones of the iron molybdates, but produced only carbon dioxide. This slide shows our XPS result, and we want to show the iron 2p3 halves peak, and we want to compare superimposed spectra of iron trioxide and iron molybdate. We see that there is a shift towards higher binding energies in the case of the iron molybdate compared to iron trioxide. Now, if we examine the molybdenum 3d5 halves region, we see that the opposite shift takes place, and now we have shift towards lower binding energies. Finally, we want to state our conclusions, and first of all, the X-ray diffraction shows the formation of iron molybdate. XPS shows slight changes in the chemical environment of both iron +3 and molybdenum +6, indicating an interaction of the molybdenum-iron interaction. MO3 by itself is almost inactive, and iron trioxide is not selective. However, iron molybdate seems to be a very promising catalytic material for the selective oxidation of methane to formaldehyde. Finally, the highest yield of formaldehyde obtained so far was 24% under steady-state conditions. We now want to acknowledge our sponsors from the Gas Research Institute. Thank you very much for your attention.
Time for one question.